Okay, so I'm going to do conditional probability part 2 today. And what we're going to be looking at once we get this thing to open up here is we're going to be looking at the use of the formula now. We looked at tree diagrams last day and how to calculate a probability of winning games. That's what we did for our examples. And conditional probability, if you remember, is the probability of an event happening given another event has already happened. Okay, and they are linked. Okay, they depend on each other, called dependent events. Okay, so we're going to use the formula to solve some word problems, okay, rather than tree diagrams, and try and see if we can do it that way today. And that's what we're going to start with today. So let me set up my page here. Okay, so this is going to be day 22. We're getting up there, getting close to the end. No, there's only one more independent events after this, and then we're done. And we're going to be looking at conditional probability. Part 2. And I think what I'm going to do is I'm going to kind of, as you probably noticed, we're getting near the end, so I'm going to kind of slow down a little bit. We are going to do the review, and we're going to do a big review before we do the hand-in and the quiz, so that, because this usually is the more challenging area, being able to remember and use the proper permutation or combination or counting principle or odds or probability. So there's a lot to deal with in it. So we're going to take some time to review those areas when we're in there. The counting section, what everybody did reasonably well in, and now we're using that as well as the probability. So that's how it's going to go when we come up. So what are we going to look at today? Today should be about a 35, 40-minute video, 35 hopefully. And we're going to be looking at using the conditional probability formula to solve problems, basically. And we're going to just do some examples. So let's just reiterate or redraw here, I guess, what that formula looks like. Okay, so it relates two events together. Okay, so if we have the probability, oops, there we go. Just setting up, there we go. Okay, so if we are looking at probability of event B given A, okay, that's equal to probability of, let's make sure we get it right, A intersect B, A and B, divided by the probability of A. Okay, so we can rearrange this. Okay, so it can also be rewritten. Well, not two L's. Also, there we go. Okay, so if we want this to be multiplied out here, we can say probability of B given A times the probability of A equals the probability of A and B. Okay, so we can have it rewritten in a single line as well. Okay. Okay, B depends on A occurring. B depends on A occurring. So the first one depends on the second one in how you write it. So let's kind of look at an example of using this formula. A lot of times we don't even write it out, we just use it. And I'll show you how that works. So an example of that, what is the probability? Let's use marker here. Put that there. Okay, what is the probability of drawing two hearts in a row from a deck without replacement from a deck of cards? Okay, so the first thing you got to think of is we're looking at what is the probability. So we have two events happening here, okay? And we have to say, okay, well, they are dependent on each other, okay? One depends on the other. They are conditional. The second heart is conditional of getting the first heart. If you don't get the first heart on the first card, you can't get the second heart on the second card and be successful. Okay, so what we want to do is we want to find, let's say that H equals getting a heart. Okay, so the probability, if we use the formula here, okay, and then H1 in the first card, we'll say. H2 will be a heart on the second card. Okay, so the probability of getting both. So probability of getting a heart on the first card and a heart on the second card. Okay, so this is going to follow this right here. Okay, that's going to equal. Okay, so it's going to equal the probability of getting a heart on the first card times the probability of getting a heart on the second card, given that you've got a heart on the first card. Okay, so this is how you say it. This is how it reads. Probability of getting a heart on the first card and a heart on the second card equals the probability of getting a heart on the first card times the probability of getting a heart on the second card, given that you've already got a heart on the first card. Okay, so now we just have to think probability. So what is the probability of getting a heart on the first card? That's where we start. Okay, so we've got favorable hearts. There are 13 hearts in a deck of cards over 52. So this is hearts, and this is total. Okay, so that's our probability right there. Now, that's where it gets a little tricky. Okay, but not too tricky. Okay, what is the probability of getting a heart on the second card, given that you've taken one heart out already? That's what this means. Given that what is the probability of getting a heart on the second card, given that you've got one already? So you've got one in your hand, so that means you've taken away one heart. So if you've taken away one heart from the deck, there are 12 left in the second draw. So this is the first draw, this is the second draw. There's 12 hearts left. Okay. And then there's 51 cards because you've taken one out of the total as well. So the probability of getting a heart on the first and second draw is going to be the product of those two. So we take our calculator out, we go 12 times 13. Over 52 times 51. Okay, 12 times 13, that's 156. And 52 times 51, I don't know. 2,652. Okay, so if we go 156 divided by 2,652, it's 1 over 17 in fraction form, or 0.0588, or 0.0588, yes. Okay, so that is an example of using probability, okay, that is dependent on each other, okay, without replacing, taking one card and then another. So when you take one card out, you've used up one card on both the top and bottom, and conditional probability means the second one depends on the first one. Okay, so that's the first type one. That's about the easiest type of those that there are. So let's delve into a little more complex example in our second one here. So let me bring that up on my other screen here. Okay, so let's do a percentage example. So this example that we're going to do now is going to be conditional probability, okay, using that same formula. But we're going to be looking at a percentage probability example. Okay, so you might not have to figure out the probability with the formula, you just might be given it. So let's sorry guys. Let's say that I got my example here. 68% of Canadians own a hockey stick. Okay. Of the Canadians that own a hockey stick, so out of that 68%, 88% are carbon graphite type. Okay. And then the question is, if I guess, randomly select a Canadian, what is the probability that they own a carbon graphite stick? So what do we know here? So we know that, let's say that for all Canadians, the probability that you own a hockey stick is H. Okay. Okay. Probability that it's graphite is G. Okay. So basically, we want to use the formula that we were talking about earlier. So if we think about what we know that the probability that you own a hockey stick if you're a Canadian is equal to 0.68. So we're going to use the decimals here. Okay. The probability that your hockey stick is graphite, given that you own a hockey stick, okay, of the Canadians that own a hockey stick, so you have to own a hockey stick, and its probability that's going to be graphite if you own one is 88%. Okay, and the question is, what are we trying to find? We want to know what is the probability that you have a graphite and own a hockey stick. Okay, that you have a hockey stick and it's graphite. Okay, so if you go back to that formula, if we want the formula written as one line, the probability of a graphite stick, owning a graphite hockey stick, having a hockey stick and it being graphite, equals the probability of having a hockey stick first. Okay, remember the bottom one goes first, times the probability that you have a graphite stick, given that you have a hockey stick. Okay, so you have both those numbers here given in decimal. So probability that you have a graphite hockey stick is the probability of having a hockey stick times the probability of hockey stick owners that have graphites. So you just multiply the two numbers together, basically. 0.68 times 0.88 equals 0.0584. 5984, sorry. Or if you like as a percentage, since the question was in percent to start with, 59.84%. Okay, so that's an example of using that conditional probability. Okay, you multiply the fact that the probability that you own a hockey stick and the probability of the hockey stick owners that have graphite sticks that are hockey stick owners. Okay, so that's the second type of question that shows up. Let's check our time here. It's about 18 minutes. So we can do our third example, deals with kind of a tree example. Okay, and sometimes they throw in complements. So like in this one here, I could have said, what is the probability that if you own a hockey stick, it's not graphite? Then you would just change this last number, 0.88 to 0.101, right? Or sorry, 0.012, okay? Because it would be 100% minus that. So let's do an example of some more percentage examples, but let's do one that might use a complement in there, okay? So this will be our third example. In this area. And then we'll do, if we have time, we'll do a population one with population numbers. Okay, so let's flip ahead. And this is still with percentages, still the same kind of example, but I'm going to throw in some not ones. And then we can use a tree diagram to help us as well. Okay, so we're going to combine two concepts that we have. Hey, Adam remembers to set his alarm, okay, on his phone 60% of the time. Okay. When he remembers to set the alarm, so that's conditional. Okay. He misses the bus 10% of the time. If he forgets to set the alarm, okay, he misses the bus 65% of the time. Okay, Adam missed the bus. Okay. What is the probability he remembered to set his alarm? All right, so this one helps us if we take the two. We can use a tree diagram to help because there's two events here, two events that are dependent on each other. Okay, there's conditional probability here, and there is because if he sets his alarm, he has a 60% chance. Sorry, 65% chance of not missing the bus, right? Okay, so let's go ahead and first thing we got to do is we got to define all our variables. Let's say setting his alarm is A. Okay. A prime, he does not set the alarm. Okay, so probability that he's going to set the alarm. Oh, well, let's do that next. Let's do the other part first, missing the bus here. Let's say that he misses the bus. And then, of course, he does not miss the bus. Okay, so we're going to use A for alarm and M for missing the bus. So now the probability. Adam remembers to set his alarm 60% of the time. So that's just PA. Okay, that's that one. When he remembers to set the alarm, he misses the bus 10% of the time. So when he remembers to set the alarm, he will miss the bus. So he will miss the bus given that he set the alarm is 10%. Okay? Miss the bus given that he set the alarm. Okay? Okay, the opposite of that we can do as well, right? If we want to, but we don't need it so far. We'll see. If he forgets to set his alarm, he misses the bus 65% of the time. So if he forgets to set his alarm, he misses the bus. If he forgets to set the alarm 65% of the time. Okay, so there is what each of those work. So when he not sets the alarm, we can do P A prime would be 0.4. Okay. Okay, now what we're trying to find, Adam missed the bus. So here's our two misses. Okay. So we have to kind of do our tree diagram. We have to have a situation where he sets the alarm and where he doesn't set the alarm. And then we got to figure out when he misses the bus. So it helps to draw a tree diagram. So we're going to do this over here. So first thing we're going to do is we want to find, what are we trying to find? We'll put up here. So we're trying to find the probability that he set his alarm, okay, and missed the bus. He set his alarm and missed the bus. Okay, how do we know that? Right here. Adam missed the bus. What is the probability he set his alarm? Okay, he set his alarm and he missed the bus. Okay, that's what we want to find. So now we have to look at that conditional probability formula and find the string that'll get us to it. So if we remember, P, A, and M equals here, P, A times, sorry, P, okay, that he set the alarm and he missed the bus, given that he set the alarm. Right? What is the probability that he set the alarm and missed the bus? It equals the probability that he set the alarm times the probability that he missed the bus, given that he set the alarm. So now we have to just do that tree. So the probability that he set the alarm is 0.6. Okay, we don't need to worry about the probability that he did not set the alarm. That's 40%. But we're not going to follow that because we have to do this one first. Okay, then we have the probability that he missed the bus. Or did I put? Oh, he's not on the bus. What is the probability he missed the bus? So this is just an M. Sorry, guys. He missed the bus. He did not get on the bus. So fix that up. That's not a prime there. Okay? Because it's the probability that he missed the bus, right? Given that he set the alarm. So we want the probability that he missed the bus, given that he set the alarm. Okay, so we look up here, that's 10%. And that's going to equal probability A and M, that he set his alarm and missed the bus. So just these two multiplied together, there's the path that we have. If we're doing the tree diagram, we could have done all of the other ones if we wanted, but this is the only one we need. So therefore, it's 0.6 times 0.10, which equals 0.06. So the probability that he set his alarm is 6%. Okay, which you can write as a 6%. Okay, so there's an example of using that formula along a tree branch. Of course, you don't have to find any of the other tree branches because it's asking for a specific. Miss the bus when you set the alarm. Okay. Okay, let's see what we got for time here. Oh, we're about 30 minutes in. Okay, so let's see what we got. I've got another example here with population numbers. And then we can do some practice. And then what I'll do is I'll do this one and then I'll leave the practice. I'll give you a work period tomorrow just so you can do some of the questions on this in section 5.5. So what we'll do is we'll do this last example, and then I'll give you the questions. You can do them if you want, but I'll leave next period open for practice. Okay, so this will be our last example, the fourth one. This is an example with population numbers. Okay, so you're going to have to pick and get your probabilities out of the total and stuff. Okay, so let's say we have 75 boys. You're looking for
Prisons.
You got them? Okay, good. Yeah, they should be in the filing cabinet there. Okay, so we got 75 boys and 120 girls live in, I don't know, let's say Townsville. Okay. Of these people, 54 boys are basketball players. And 88 girls are basketball players. Okay, so this is a bit of conditional probability. Okay, and you got to be careful because you have to know the total. So you're going to have to add both the boys and girls together and all that kind of stuff. So that's what we're going to be careful with. So I'm going to ask a couple of questions with this one. If a person in Townsville is selected at random, find the probability that the person plays basketball and B, that a basketball player is female. That are a basketball player and female. Oh no, I had it right the first. No, I got it right. That's good. I'm confusing myself already. Bad. Okay, so we're just going to be using numbers here. So we'll solve this one. Okay, so first one's fairly easy. The person plays basketball. So we need the total outcomes. Which would be people. That equals 75 plus 120. So the total number of people in the town, whether they play basketball or not, is 120 plus 75. So that would be 195. Okay, so that's a total. Now we need the person plays basketball. So basketball players. So we need the basketball players. Okay, the basketball players are going to be 54 boys and 88 girls. Okay, so 54 plus 88, we've got a total number of basketball players. Okay, so what's the probability? We got favorable basketball players over total. So favorable probability of a basketball player equals favorable over total. Okay, it's not odds, so be careful. So that would be 0.728. Okay, so that's just using numbers. Okay, that they are a basketball player and female. Okay, so we have to take all the female basketball players out of, given that they are basketball players. So the total outcomes possible is only basketball players. Okay. Oh no, it's going to crash. I hate when this happens. Sorry on this one, guys. The notes are, you're going to have, hopefully you were taking notes because this has been giving me problems all day today. Stupid game. It will recover everything except it probably won't recover that last question. So hopefully you were taking notes because I won't be able to post the notes for this video. There was a crash, as you just saw. It'll recover up to, but not that last page I was doing probably. Sorry, guys. Yeah, so we got, and we didn't get the basketball question. So hopefully you had the notes on the basketball question. So we were doing B. Okay, so I'm just going to pause the video here and rewrite everything down that I had, or try to, and then I'll restart the video from where we were. Okay, let's try again. Okay, so the person that a basketball player is female, hopefully that's what it was. So we have to get only the total is only basketball players. You have given that. Okay, total is only basketball players. Okay, because you can't pick. It says that a basketball player is female, so they're just looking at the total number of basketball players, not the total number of people in the town. So the total number of basketball players is our bottom. So the total number of basketball players was 88 plus 54 for basketball players. Okay, and that was 142. Okay, and then girl basketball players are favorable are girl basketballs players. Okay, and that equals 88, I think. Yeah. So our probability that a basketball player is a girl is 88 over 142, which in this case is 0.62. Or we can reduce that down to 44 over 71 if you want to leave it as a fraction. Okay, so I'm going to leave you with the work period for next period on this conditional probability section 5.5. So 1, 2, 3, 5, 6, 8, 9, and 14. So you don't have to do it this period. If you have time, you can. But that's what you'll work on next day, those 8 questions for practice on page 350 to 352. There's a few more there as well. And good luck. And that'll be a work period tomorrow.